Rihanna Martin, and today I'll be talking about the project I worked on this summer with my partner Jonathan Barros on simulating the effects of evolution on Nectar microbe metacommunities. Now here's our poster that I will be explaining in greater depth throughout the presentation. In our project, we focused on creating a simulation model to address the following research question. How would changing priority effect strength across the flowering season change the community dynamics in the meta-community? Now you may be wondering why we chose to take a simulation approach. Well, we wanted to be able to create predictions of what is happening in the field without having to do direct experimentation. We used an existing simulation model that was made by a former Stanford PhD student, Jiwon Song, and modified it to include the parameters we were investigating. Now I'm going to explain most of the parameters in the base simulation that Song wrote. In the base model, there are flowers that get pollinated by hummingbirds and bees. These pollinators carry microbes that are put into the flowers, which will then either be colonized by yeast, bacteria, co-dominated, or no microbes. And at the beginning of a flowering season, the flower is not colonized by any microbe because it has not been visited by a pollinator yet. And when the pollinator comes to get nectar from the flower gets inoculated. The flower then will be colonized by either bacteria, yeast, or both. And non-colonized flowers later get introduced to the community. Now, as before, a pollinator will come and pollinate the flower. In this case, because the pollinator visited a flower that is bacteria-dominated, the new flowers that surround it have a high probability of becoming bacteria-dominated flowers as well. And these events of pollination are happening across the landscape and are connected via a meta-community. A meta-community are many individual communities connected by dispersal. Now the original plot shows the relative abundance of colonized and non-colonized flowers in the meta-community. The trend here is that the percentage of flowers in each category stays approximately the same throughout the flowering season. But what about priority effects? Song simulation doesn't take into account that a community that starts with some microbe may change community states. The order of arrival of the microbe is extremely important in determining the dominance of the flower. For example, if a flower is yeast dominated first, and then a new pollinator comes along carrying bacteria, the likelihood of that flower becoming bacteria dominated is very low. It is more likely that the flower will become co-dominated by both yeast and bacteria. So we modified song simulation to build in this change in community state. Here's an example of a flower that starts as yeast dominated, but it could have started with bacteria. Over the lifetime of the flower, there is a probability that the flower will transition into another community state. Now the first possibility would be that the flower would not change community states. There is a high probability that the flower will start and end being yeast dominated. The next possibility would be that the flower would transition entirely from one state to another, and there is a very low probability that a flower which started off being yeast dominated would become bacteria dominated. And another possibility is that the flower would become co-dominated. There is a higher probability that this would happen. And the last possibility is that the flower would end up containing no microbes. Now, over the course of the flowering season, we hypothesize that the yeast evolves to resist the effects of bacteria. This decreases the probability of bacteria becoming dominant and therefore increases the probability of yeast-dominated flowers. And this rapid evolution of the yeast impacts the probability of a flower changing community states. At the end of a flowering season, the yeast has evolved to not be affected as much by priority effects. Therefore, the probability of a flower changing community states would decrease as time goes on. This represents a meta-community at the beginning of a flowering season before the yeast has evolved to resist priority effects. And we expect to see that the yeast evolves to be more resistant to other microbes as the flowering season goes on. So returning back to the original model, we see that the level of flower abundance stays the same for all categories. In the new model, because we added in the evolution parameter, we expect to see all the different categories to change. For instance, because the yeasts are evolving, we expect the number of yeast-dominated flowers to go up, whereas the number of bacteria-dominated flowers we expect to decrease. However, I want to emphasize that this is hypothesized results and we are still working on finishing the code for our simulation. And lastly, we conclude that rapid evolution might dramatically influence what we see in the community. This theory can be applied to various situations and communities, and the simulation is a great way to help us understand what is happening in the field even though we can't do the experiment. Lastly, we would like to thank our amazing mentor Callie Chappell and Stanford professor Dr. Tadashi Fukami for their support and guidance throughout our research experience. We would also like to recognize the members of the Fukami Lab and a special thank you to the members of the Team Nectar Microbe.